envy your biking. Hi, good to see you, John. Yeah, yeah. How often do you pump those tires?
Not enough. I actually have a bike pump in here.
Oh, yeah, right, right. I can't get any of that now, can I? We can't interfere with it?
No.
It'll drip. Okay, then we'll wait. Okay.
Oh, yeah, you can. There's a little stop drip.
Oh, you can?
Hour
Okay.
or so.
Is it going to be too strong? It's too strong anyway, right, usually?
I tried to make it a little weaker.
That's good. I'll take a little more, actually.
Yeah, take as much as you want.
That's probably all I want, yes. Great. Is that in the right place? Yeah, okay, good. Okay, I'm going to get started. Okay, we should get started. This is the last class before the final on Monday. We'll go over a few administrative things later, but let me go over the review as I usually do, bringing you back to the GMM that we started last time. By the way, is it working okay now, Hit? Is it? Great, okay. So remember, this is the particular picture we wanted for GMM. This is GMM now. We backed up a little bit. All of the pertinent variables here. And in red, I've indicated the things you should know. They might appear on the final. If you forget these formulas, you can buy them if I need them. I haven't set up the exam yet. Remember, you can buy. So I don't want you to be frightened you forget a critical formula. But these things you should remember. You know, the exponential and geometric behaviors so fundamental to GMM. For GM1, we got that waiting time distribution right here. For GMM, we get, again, an exponential with the constants a little bit different. And the mean weight in GMM is right here. Fine. And by the way, you should focus on the other lectures and the things that I pointed were important. Usually the red equations I expect you to know. Polachek-Kinchin, some transform things, etc. We'll talk about that later. Okay, so GG1. GG1, we had some very nice definition. This key variable U, difference between service time and inter-arrival time. Able to write down that the waiting time equation is basically this one. And in shorthand notation, it looks like this, using that plus notation where the plus means maximum 0 and the variable. And then we started to look at a recursive expression for Wn itself, finding it basically from this expression up here. And so we started iterating, and we went a distance. We found that Wn looks like this thing. Namely, it's a sequence starting with 0, then one of the u's, then two of the u's, then all of these u's, plus finally the initial waiting time. And we found out we could define a new random variable, Wn prime, which looks exactly like Wn, except we've changed the subscripts. So we started with the high levels up here at n-1. We started with 0 here. So one of them, two of them, three of them, one of them, two of them, three of them, all the way out to all of them. Well, here is all of them down to n-2. Then when we add n-1, we add W0. That's the unusual case there. We then made the obvious definition. We may as well sum those little u's into a big U. So we define capital U sub n like that, with an initial value sub 0 defined to be 0. And then this basic equation up here looks like this. It's the max of a bunch of capital U's. And of course, U0 is 0. We also pointed out that this key random variable between service time and inter-arrival time in the limit has a value, and it's related to the typical service time and typical inter-arrival time random variables. And I made the point that if we have a stable system, if it's ergodic, namely if we're always less than 1, namely if the expected value of un is less than 0, and having the expected value of un less than 0 means that the expected value of x bar minus t bar is less than 0, shows that rho is less than 1. Okay? In that case, the limit of these two random variables, wn and wn prime, both have the same limit, and the limit to the basically the waiting time random variable that we're trying to find. We want the distribution of that waiting time of the random variable here. So going to that limit, we had defined that the limit of the wn distribution will have the same limit as the wn prime distribution, and we define that limiting variable as w now without a subscript. And basically, this is the thing we want to find. What is the waiting time distribution as we go to the limit? And I pointed that right here. That's what we're seeking to find. The last time we found out that the PDF for this random variable we call capital C, and its density, the derivative of the derivative, the PDF, is written this way. And from the definition, and we went through a little calculation, we showed that, in fact, the density on this random variable u is the convolution of the service time density and the inter-arrival time density with a negative argument. And if you recall what convolution is, it looks like this. And we're going to focus on convolution as we move ahead. Okay. So having said that now, what we really want is this probability, this waiting time distribution. Initially, it's wn of y. We define that to be the probability that wn itself is less than or equal to y. And in the limit, we're going to get the capital W. Now, writing down wn plus 1 of y from that original definition up here, namely that early description we had up here, we can write the following. That's equal to the probability that what? That wn plus un is less than or equal to y from the definition I just showed you. And let's write that down now as a conditional, use our usual trick. So leave space for an integral for a moment. We're going to take the probability that that quantity, u sub n, is less than or equal to y minus w, given wn equals w. That's the condition I'm putting in. And then I'm going to uncondition by multiplying by the probability of that condition. Let me move this over a bit. Without messing it up. Let me clean this up a bit. That's the wn of w over all possible values of that from, in fact, 0 minus to infinity. And I'm specifically saying 0 minus. I'm not going negative. Why not? Because the waiting time can't be negative, so the probability of that is 0. And I choose 0 minus because there might be a step function at the origin. I want to be sure to include it. So I want to be sure to go slightly to the left of that origin. Okay, but this says un less than or equal to y minus w, given the waiting time for the end customer. But this un, service time and an inter-arrival time, it's independent of this waiting time, so we can get rid of it. So that says that wn plus 1 of y is this integral 0 minus to infinity of simply And what is the distribution for un? I wrote on top of the page. I'm going to use that now. That's capital C sub n of y minus w. And then I have to uncondition again dw sub n of w. And this is only for y greater than or equal to 0, of course. And of course, in the limit, wn plus 1 of y and wn of a function, both of those go to the same limit. We call that w itself, right up here. They all go to the same distribution, single name w. So let's write all that down. That means that on the left-hand side, we're going to get w of y is equal to the integral from 0 minus to infinity of capital C, and I may as well get rid of the subscript on C as well, so I don't need C sub n, of y minus w dw of w. And again, that's for y greater than or equal to 0. Now, it's also true for y less than 0, what is w of y? It's 0. The probability of having a negative waiting time is 0. That means that this function, w of y, can be written as a two-part expression. It's integral, that integral itself, 0 minus to infinity, capital C of y minus w, dw of w. And that's for y greater than or equal to 0. And it's 0 for y less than 0. This particular equation, I'm going to move it down just a little bit, is a key equation. And it's called Lindley's integral equation. Let me mark it as special. After David Lindley. Lindley's integral equation. And as I mentioned the other day, it's an integral equation of what's called the Wiener-Hopf type. It's not an unusual expression. Let me clean this up a bit. Now, we can write that question, yes? W. What is u? It's a service time. It's drawn from b of x minus t into arrival time drawn from a of t. For the end customer, it doesn't matter how long that customer is going to wait. And by the way, sometimes GG1 is written as GI/G/1, the I standing for independent, meaning that the service time and the interarrival times are independent. We've been assuming that without being explicit about it. I'm being explicit now. And that's part of the reason we can do this. There's a whole other set of theory if there was a dependency. And any dependency really throws this system into trouble. The analysis just goes to heck. Okay, now we can write this in two other ways. One thing we can do is we can integrate by parts. This is integral of u dv. That's equal to uv minus the integral of v du. That's the integration by parts rule. So let's do that. So first of all, for y greater than or equal to 0, we'll get that w of y is equal to, now this is uv, will be capital C of y minus w. And v is capital W. evaluated from 0 minus to infinity, and then integral of v du. And that'll be the integral from 0 minus to infinity again of capital W, that's v, dc of the argument y minus w. That's the result of the integration by parts. Now I have to take the limit from 0 minus to infinity of these things. So that's equal to the limit as w goes to infinity first of c of y minus w, w of w, plus, well, limit, I don't need a limit now, w going to infinity, so let's just add to that. Plus the other limit is simply going to be c of y, w0, times w of 0 minus. That's where the minus was needed. Plus the integral. And this is an integral from 0 to minus to infinity. W of w dc of y minus w. Okay, now let's see what's going on here. When w goes to infinity, if w goes to infinity, then we're talking about capital C of minus infinity. And the only way you can go negative is for the interarrival time to go negative. And in fact, that would assume the interarrival time goes to infinity, which is 0. So this first term goes to 0. And what is w of 0 minus? What's the waiting time for a slightly negative waiting time? 0. So this term goes to 0. So we're left with just the other piece. So the other form of Lindley's integral equation is the following. Again, it's a two-part equation. It's what's left here, this integral at the end of this equation. It's 0 minus to infinity w of w the c of y minus w. And this is capital C here to make it even bigger. Or 0 in the range y less than 0 and y greater than or equal to 0. That's the second version of Lindley's integral equation. So let me indicate that. Question? Oh, I'm sorry, you're right. This is negative right here. You're correct. Right there? Yes. But it is. It is. It's the upper minus the lower. Okay. Yeah, but I've got the, when I differentiate C, y minus w on w, another negative sign comes in. When I've gone from, so you got two negatives. You're quite right. There should have been a minus with a minus, but that's where the plus comes from. Okay. Now let's change variables to get another version of this. I'm going to let u be the obvious. Okay? And what am I going to get then? I'll get that w of y is equal to, once again, the integral. It's going to go from minus infinity to y of capital W over W, I'll put in y minus u, dc of u. This is for y greater than or equal to 0, and 0, y less than 0. And this is the third form of Lindley's integral equation. And you see everything is depending upon the input variable here is capital C, service time minus inter-arrival time. Now when you look at this last form, that equation looks like a convolution, but not quite. Why is it not W of y equals a convolution of a couple of things? What's missing? What's missing is the fact that it's 0 here. But it's almost a convolution. We're going to fix that in just a minute, because we know what to do with convolution, okay? Now, we have to solve this equation. If we solve it, we know capital C, we're looking for capital W. Find a way to solve it. And the approach we're going to use is basically, it's called a spectral solution. Spectral in the sense of frequency. So L-I-E, Lindley integral equation. And we're going to use something called spectrum factorization. So I'm going to do what I just said was wrong with this equation here. I'm going to find the other half of that convolution. So let's define, let's actually say that. The other half of the convolution. Namely, I'm going to call it capital W sub minus of y, which would be the other part of this expression, namely, it's 0 for y greater than or equal to 0, and it's that integral otherwise. It'll be the integral from minus infinity to y of w of y minus little w dc of u. It's y minus u. We change that. It's y minus u dc of u. And that's for y less than 0. Which means that if I add these two, the w without a subscript, you could call it plus if you like, and w minus w of y plus w sub minus of y is just that integral. Minus infinity to y of w of y minus u dc of u. And I'm going to write that instead of dc of u, I'm going to use the density instead of distribution. That's supposed to be a smaller lowercase u. And this is now for all real y. And that's an important equation we're going to use. I'll give it a name. In my notes, I called it this thing. I called it a double exclamation mark. We'll refer to it later. So now we're getting somewhere, because we know what to do with convolutions, okay? Now, again, I'm going to take you down into some convex analysis. And with notation, and I'm going to introduce some notation. I've already introduced w minus of y. Where the heck did that come from? We're going to get rid of it eventually. But I have to make some assumptions to make this operate properly. So we're going to assume the following. Some assumptions. Oops. And I warned you last time, happily, and I'll tell you again, when we come out of this deep dive, we'll have a very nice algorithm. And by the way, I've assigned you another homework assignment. It appeared today. It's due Saturday night. Do it, because it's going to take advantage of this approach, and that's what I want you to get out of Chapter 8. Okay, so that's a clue about the final, okay? Yes? It came on at 2 o'clock. Have you, anybody seen it? Oh, good. I didn't want it to pop up before I could tell you it's coming, out of kindness. I can be kind occasionally. Okay. Okay. So I'm going to assume the following, that A of t, the interarrival time density, has a certain behavior. I'm going to say it's capital O of e to the minus dt. And this is from some positive d. That means that the limit, as t goes to infinity, of A of t over e to the minus dt is itself less than infinity. So basically, A of t drops off at least as fast as an exponential for large t. Large t, A drops off at least as fast as that exponential. Okay. And by the way, this is for some d greater than 0. Okay. So the behavior of capital C of u is governed by A of u, A of t. And you can show that the limit as n goes, excuse me, as u goes to minus infinity, of the quantity capital C of u over e to the plus du, that too is less than infinity. And these are all reasonable assumptions, the A of t limiting going down by an exponential. And we can argue why this is true. I don't want to go into the details right now, but this will also imply the following, that the limit as y goes to minus infinity of w sub minus of y over e to the plus dy is itself less than infinity. All that coming from this first assumption up here, which is A is O of e to the minus dt. Okay. Now comes a new definition. I want to define something called phi sub minus of s as the Laplace transform of w minus of y. Okay? It's the integral from minus infinity to infinity of w minus of y, that's a moment ago, e to the minus sy dy. It's a Laplace transform. And it will be analytic for the real part of s less than d. And also define phi sub plus of s as the Laplace transform of the w of y. Okay? Integral from minus infinity to infinity of w of y e to the minus sy dy. And that's the Laplace transform of the waiting time distribution. We want that. If we can find it, we're done. Because that will give us w of y, which is what we're looking for. And by analyticity means there's a unique derivative in the region for which it is said to be analytic. Okay. Now we already had the following. We had defined W star of S as the Laplace transform of the density of the waiting time. Let's write that down. Integral, we chose from 0 to infinity because waiting time can't be negative, of little w of y e to the minus sy dy. So the thing on top is the transform for the PD, capital P, capital D, capital F, and the one below now is for little p, little d, little f, the distribution and the density. So those two are related, in fact, so we can say that S times phi plus of S is equal to what? Anybody recognize that? It's a derivative. S is a derivative, so what is the transform? It's the Laplace transform of the thing for which phi plus is, which means it's equal to W star of S, because that's the transform of the derivative of capital W. Now, let me just point out, you'll find that property in table I3, item or entry number 11. And those of you who are familiar with Laplace transforms beyond what we've done, when you multiply by S in the frequency domain, you're differentiating in the time domain. When you divide by S in the transform domain, you're integrating in the time domain. And we prove that actually in the book. You'll see it in the Appendix A. Okay. Now, since, coming back up here, W minus and W itself have 0 regions, then these integrals are clipped over a half plane. So let's write that down, okay? That means that phi minus of S, let's write that one down again. Phi minus of S is only integral from minus infinity to 0 minus. We could have seen that earlier, of W minus of Y e to the minus sy dy. And similarly, phi plus of S is the integral from 0 minus to infinity of W of Y e to the minus sy dy. So far, fairly simple observations. Now, W of Y is a distribution function, namely is a PDF, so it's limited. And it's bounded as y goes to infinity. What happens as y goes to infinity? What value does it take on? 1. So we know it's bounded, okay? That's important. That implies that its transform, phi plus of S, is analytic in real part of S less than D. Let me say that in words. Less than D. And A star of minus S is analytic I'm sorry, this is greater than 0. Please change this over here. I meant that's greater than 0, of course. This is analytic in the region real part of S less than D for some D, positive. And that's also true for phi minus of S, for the same reason. Now let's recall something about little c. C of u, the density, what is it? I opened you up with that. It's A of minus u convolved with B of u. So its Laplace transform, C star of S, is equal to what? It's equal to the product of the transforms of each, but I have a minus u for A, so it's A star of minus S times B star of S. Now, if you look at W of Y plus W sub minus of Y, let's go back to that equation. This double exclamation mark equation, it's a convolution. It has an upper limit because W can't go negative for negative values. It has to be 0. That's a convolution itself. And it's a convolution of capital W and little c. So this itself is a convolution, as I just said, of capital W of Y and little c of u. So transform that baby. What's the transform of capital W? It's phi plus of S plus the transform of W minus is phi minus of S. And that is the convolution of those two. Well, what is the transform of capital W of Y? Do we have a name for it? Top of the page. It's phi plus of S, right? And what is the transform of little c? I wrote it right here. Okay? So it's A star of minus S, B star of S. Okay? Which means that phi minus, let's factor out the phi minus of S, is equal to phi plus of S times what? A star of S of minus S, B star of S minus 1. Now it turns out, as we said before, that phi minus of S and A star of minus S are analytic in the region real part of S less than D. And similarly, phi plus of S and B star of S are analytic in the region real part of S less than 0. Greater than 0. So one is analytic to the left of a positive number, and the other one is analytic to the right of the argument. Yes. Oh, sorry. Yes. 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 Come back up here. I'm transforming this equation. This one up here. That'll give me phi plus. That'll give me phi minus. And this is a convolution. That means it's the transform of this times the transform of that. So let's go down and find that. Which equation were you after now? It was this one here, right? So that's the transform of W star. And I just showed you the transform of C star is that. That's because up here I need the sum of the two to get the pure convolution. This gave the phi plus, this gave the phi minus. Okay. Now comes the spectrum factorization part. I need to find something about the one item I know. I know what this is. That's given. That's the input of the system. That's GG1. So I want to basically find the proper representation of that quantity. Of A star of minus S, B star of S minus 1. And I'm going to do it as a product of two factors. And before I tell you what it is, let's remember that we can represent any interarrival time density and any service time density using the method of stages from Erlang, which involved analytic functions, ratios of polynomials, as closely as I like. Remember we had that Cox situation or the series parallel situation. We can approximate it as closely as we like. So we're going to assume that A star of minus S, B star of S is in fact a rational function, okay? So I'm going to write this quantity that I'm after now, A star of minus S times B star of S minus 1, as a ratio of two new quantities, psi plus of S, and you have to listen carefully how I say that, over psi minus of S. I want to find those two with certain properties. Now this clearly, I'm going to make those each of those a polynomial in S, so that's a rational function now, that ratio, okay? And I want a particular form for those guys. It's going to be the following. Now notice, I'm introducing more and more notation on you. I got the phis and the psis. Sorry, but when all done, you see how valuable it really is, okay? So don't let the notation get you too badly, except if you can't read my writing, that'll be a problem. Okay, okay. Here's what I want. For the real part of S, in the positive half plane, greater than 0, I want psi plus of S to be analytic. I'm going to ask for that, with no zeros in this half plane. Namely, there's no poles or zeros in the right half plane. In this half plane. And similarly, for the real part of S less than some number D, I want C minus of S to be analytic. Again, with no zeros in that half plane. You'll see shortly why we want to do this. Now, in addition, I'm going to want the following. For the real part of S greater than 0, I want the limit as absolute value of S goes to infinity of C plus of S divided by S equal 1. Its limit should be 1. And for the real part of S less than capital D, I want the limit as, again, S goes to infinity in absolute value of C minus of S over S equals minus 1. I'm going to want to find C plus and C minus with these properties. Okay? That's the hard part, which means I have to find the zeros and the poles, literally the zeros of these polynomials. Once again, that's our hard part. And it's the only hard part, factoring a polynomial. Okay? So let's bring this to conclusion now. So let me just point out, hard part is finding the roots of these guys, of C plus and C minus. Now, suppose we do find the C plus and the C minus with these properties. Then what do we have? We have basically that C, the phi minus of S, is equal to phi plus of S. And if you look up before, what was that ratio? We have this up here. We have phi minus equals phi plus times that product, AB minus 1. Okay? But what is AB minus 1? It's this. So what I'm trying to write down now, I'm going to multiply by C plus divided by C minus. Now, all this looks like nonsense in some sense. I'm introducing, just a second. Okay. Well, why did I do all this? Well, you're going to see in a minute. Let me rewrite this in a trivial way. That says that phi minus of S times psi minus of S is equal to phi plus of S times psi plus of S. And we talked about the region of analyticity for these quantities. I said that the psi's have to be analytic in certain regions. And I showed that the phi's also were. So in fact, there's a common region of analyticity. Namely, unique derivatives. And where is that? That's in the region 0, less than real part of S, less than D. Oops. So we can do what's called an analytic continuation of these functions. And you may or may not have heard of that before, but hopefully you have. The analytic continuation of these functions have no singularities, these pairs. In the entire, by continuing, in the entire S-plane, entire complex plane. So that means that both of those products, phi plus of S times C plus of S, is equal to C minus of S times C minus of S is analytic and bounded. And we're going to Kleinkrup's variable theory here. I'm drawing a lot of it out for you. Is analytic and bounded in the finite S-plane. And now we apply something called Louisville's theorem to show this function is a constant. And I'll give you Louisville's theorem in a moment. And that's what I wanted to be able to show. Louisville's theorem simply says if a function f of z is analytic and bounded for all finite values of the S-plane, then it is itself a constant. You can look that up and the proof is a little bit sloppy, but that's a known theorem. Okay. That means that these pairs, phi plus of S times C plus of S, is equal to phi minus of S times C minus of S equals a constant. So we're getting close now. That means that phi plus of S, the guy we want, is equal to capital K over C plus of S. And that's an important equation. We're going to use it in just a moment. This is what we want. We want phi plus of S, because it's a transform with the waiting time distribution. And that's what we're seeking. So if we can find C plus of S with the properties mentioned above, we've got it. Now, while we're at it, let's find out what this constant K is. Okay? Let's find K. You turn off the alarm, by the way? It rang? Okay, we'll take a break, because she wants to. Okay. Come back in 10 minutes, please. Okay. We're coming out of the noise now. We're gonna come back and get a breath of fresh air.
Quick question about the intuition behind U. I remember we went over it last class, but I was trying to think about it again, and I don't quite understand what it represents. So I know that it's like xn minus tn plus 1,
Right.
which is like the service time minus like
Inter-arrival time.
the inter-arrival time. But like, I guess besides for computation, like,
So physically what it is,
yeah.
x bar or X itself. It's how
Yeah.
much work a customer brings in.
Yeah.
It's a service time. You arrive, you say, I
Yeah.
need so many seconds of service.
Perfect.
After you arrive, next guy comes in.
Yeah.
How long? Tn plus 1, right?
Yeah.
That's how much time. If that amount of time is on average more than the work you demand of the server,
Yeah.
he can keep up.
Yeah.
So the difference is the amount of living space you're giving the worker. And that has to be greater than 0. That's why rho has to be less than 1. The same argument. You have to give me enough time to work on the work you brought in. And it has to
So
be,
wouldn't you want that to be less than 0? Because you want t of n plus, like, don't you
I
want
want
it to
t,
wait?
I want Tn to be longer than x. So x minus t has to be less than 0.
Yeah, okay, yeah, x minus
Yeah.
equals
Right.
Okay,
So that's the physical intuition why it's an important random variable.
okay,
And it's the input random variable.
yeah,
And as you saw from the expression, it's all that matters for w. It's not x and t by itself. It's the difference that appears in the equation defining wn.
okay, perfect. Thank you.
Sure. Okay. Up. Come back. Look, we're almost out of the woods now. I've taken you down the garden path here. Okay, so this is a critical equation. We're going to find C, but what is K? And that's the next job, okay? So let's remember that S phi plus of S, that's equal to W star of S, Laplace transform of the waiting time density. And that, by definition, is the integral from 0 minus to infinity of e to the minus sy, and I'll use capital dw, capital Y of y. Okay. Now let's take the limit as s goes to 0. Let's do it on the right-hand side, okay? So we'll get the limit as s goes to 0 of that integral e to the minus sy dw of y. And what is that going to be? Well, e to the minus sy is going to 1, and I'm integrating the distribution of the density, so that's equal to 1. Okay? So, going back to the top equation, the limit as s goes to 0 of s phi plus of s is itself equal to 1. So let's take that, take the limit as s goes to 0, s phi plus of s is equal to the limit of what s phi plus is, and that's basically equal to what is phi plus? It's k over psi plus. So that's s k over psi plus, and that's equal to 1. So we can say that k is equal to the limit as s goes to 0 of psi plus of s over s. Now, we can make a Taylor series expansion of this quantity as well, and I want to take you through the expression, the calculation, but I'll just say also, we can show that k can be written another way. It's a limit as s goes to infinity of psi plus of s, psi plus of s, and may as well try to derive it. That's the limit s goes to infinity. Now, of course, we've got that this quantity is itself psi plus over s, so we'll get s times the integral 0 minus to infinity of e to the minus sy w of y dy. And if you make a substitution that sy equals x, I'm not going to take you through the algebra here. Let me just give you the final result, because it's just, we don't have time to go through it too far. We'll get basically that k is equal to, happily, just w0 plus. The waiting time just past the origin. So there's more than one version of a k itself. I'll put that up here as well. And what is W of 0 plus physically? The probability the customer does not have to queue. You got the impulse of the origin. That's the value right there. Okay. So let me give you a summary here, and then we're going to go an example. Okay. Step 1. Do a spectrum factorization. For psi plus of s, which comes from the equation a star of minus s b star of s minus 1 is equal to psi plus over psi minus. In other words, do that factorization in this equation ab minus 1 equals psi plus over psi minus, and find the psi plus portion of it. Okay? Then we got to find from that phi plus of s, the guy we're after, is equal to something related to the psi plus we just found. It's k over that psi plus. Then find k. I gave you a couple of ways to find it. There's actually one more way. It's related to the derivative of C plus. Anyway, you find K, some simple way. Okay. What's the last step once you've done that? Invert C phi plus of S, and you've got W of Y. And you're done. So the whole part is number 1, do a spectrum factorization. And by the way, you could do this whole thing using C minus instead of C plus. It's an alternative way. It's very similar. So let me finally, and by finally I really mean that, let me give you an example so you'll see all this operational. And you don't have to remember all that complex variable theory. That was just showing you how to get to this algorithm. The trick is we got to find this C plus of S in a certain way. So let's use MM1. Okay. Okay. What is A star of S? Somebody? Yes. Boy, you can do more than just by inspection. That's good. Lambda over S plus lambda. And I'm going to ask you to give me also B star of S. Okay, so you didn't just memorize the other, you really knew it. Good job. Okay. So the next step is write down A star of minus S, B star of S, minus 1. Let's write that out. That's equal to lambda over lambda minus S times mu over S plus mu, all of that minus 1. And you do the tiny bit of algebra, and you'll get the following ratio. You got S squared plus S times mu minus lambda. Over the two factors, lambda minus S and S plus mu. That means that the thing we're looking for, we just factored this, we have to break it into two pieces now, but the ratio psi plus of S over psi minus of S, we just cooked up, that's AB minus 1. That's equal to this quantity, which is S times S plus mu minus lambda over lambda minus S, S plus mu. Now, I got to worry about where these singularities are in the S-plane. Less than capital D, greater than 0. So guess what we're going to do? We're going to draw a plot of these poles and zeros. And that's the mechanical part of this. So let's actually draw the S-plane. This is the real part of S. This is the imaginary part of S. And let's see now. Where are the zeros of this thing? Well, there's one at the origin, S equals 0. So I'm going to draw this in red. There's a 0 right there. And where's another 0? Lambda minus mu. Is that positive or negative? Mu is bigger than lambda. Service rate bigger than the arrival rate. Question that you asked earlier. So it's over here somewhere. So let's put it right here. And that's lambda minus mu. Oops. Okay. That's the zeros. What about the poles? Well, they're obvious. One is at S equals lambda. Okay, so let's put it over here. Let's say it's there. I'm not drawing this scaled, by the way. Actually, it should be closer to the origin than the 0. And where else is it? S equals minus mu. So let's put that right over here. And I'm drawing a pole as an x. Okay. The roots were easy in this example. They've already factored in the denominator, you see. They can be more complicated. You do what you can to find the roots, either numerically or Pythagorean theorem or whatever. Okay? Okay. Okay, now let's ask ourselves. Remember, we have to play with things. We said that C plus of S, I'm going to write this out so you'll see it. C plus of S is analytic, namely no poles, and 0 free. That's what I asked for. In the real part of S, greater than 0. The real part of S is to this region here. So C plus can't have any of the garbage there. Strictly greater than 0. But it can take, let me draw it in blue, let's say. C plus of S can have any garbage, namely the pole is 0, in that region. It can't have anything to the right of the vertical axis. We can have all that garbage. So those three, 2 zeros in that pole, belong to C minus. And similarly, so let me just write that down. I'm going to say C plus of S can contain this stuff. And in this other region, I'll draw this in green. Okay, C minus of S has to be clean for the real part of S less than D. In fact, I drew that green badly. Let me undo that. I have to draw a line right here. And the region C minus, but it can't take that pole at lambda, because that's clean for real part of S less than D. And I'm going to choose D to be at lambda. Okay? So C plus of S can take all of this stuff. And let me write it down to remind you what it is. It says C minus of S is analytic and zero free, namely no poles and zeros, in the real part of S less than D. And D has to be any number greater than 0. So, in blue, what is C plus of S? It could take everything in the blue region, right? And that's 2 zeros and a pole. Let's write that out. It's equal to S times S plus mu minus lambda those are the 2 zeros, and the pole is at minus mu, so it's S plus mu. And I'll draw it as a picture over here. C plus of S looks like this. It's got the 0 here, the pole here, and the other 0 here. That's it, got 0. That's at lambda minus mu. And minus mu. And in green, C minus of S is simply the one thing that's left over. It's the 0. It's basically the pole, but it's, remember, C minus is in the denominator, so it itself looks like a 0 there, so it's lambda minus S. When S equals lambda, in the denominator, that becomes a pole. And so C minus of S looks like this. It's basically got a pole right there. So in green, this is C minus of S. And in blue, this is C plus of S. Question? Yes? Yes. So it has to be clean, not where the blue is. It can have anything in the blue. It's got to be clean to the right of that vertical axis.
So I'm confused why C plus of S is not the green area, but the blue area.
I didn't hear the question. Say it again.
I'm confused why this C plus of S is the blue area, but not the green area. Because you actually want, like, you want the real part of S to be greater than 0 for C plus, right?
No. I want it to be clean. I want C plus to be no poles, no zeros in, I'll just draw the, here, anywhere there. And that's not the blue. The blue is where it can have all the garbage we want, and I'm going to put all the garbage that's there into C plus of S. It can't have any poles and zeros in this region I just drew.
Also, if you include the lambda minus S term as well, then it would have a pole.
It would have a pole and be a part of S greater than 0, and that would fail. And similarly, why the blue, okay, the blue can't, the C plus of, the C minus of the green can't take anything basically in this whole region. Real part of S less than D is going to be this. So it can't have anything here, but notice C plus took it all. It can pick up this baby here though. So it's really quite mechanical and simple when you're all done. What was the hard part? Finding those roots. But that's all it is. So, you can forget the Louisville's theorem and some of the analyticity and the fact that it's a constant region. It was all to get to this algorithm. And this is a very simple one to do, okay? And by the way, we had a couple of other conditions, if you recall, for C minus and C plus. Where are they now? In addition here, okay? Let's check that these things are true. So let's do that down here. Okay, let's look at the limit of c plus of s over s in the limit as s goes to infinity in absolute value. Well, c plus of s, take the blue equation above, divide by s, let s go to infinity. What do you get? You get 1, just like you're supposed to. And similarly, the limit as absolute value of s goes to infinity for c minus of s look at c minus of s, divide by s, you get minus s over s, which as s goes to infinity, it goes to minus 1. Sure enough, those are the conditions we needed. Okay? Let's do k. Let's use k in the following version as the limit as s goes to 0 of c plus of s over s. That's the limit as s goes to 0. Let's see what c plus of s is. Well, I get rid of the s, so it's s plus mu minus lambda over s plus mu. What's that limit? It's simply mu minus lambda over mu, which happens to be 1 minus rho. Remember, I told you it was also W0 plus. The probability you don't weight. In MM1, you don't weight probability 1 minus rho. Okay? So when you're all done, you've got to basically invert this baby. Okay? So we got phi plus of s, the thing we're after. That's a transform of the distribution, is equal to k over psi plus, and that's equal to 1 minus rho upstairs times s plus mu over s times s plus mu minus lambda. Those are the two poles in the root 0 that I had. Well, we've seen this before, it turns out. If you invert that, and you can do this in your sleep now, can't you? Okay. That's 1 minus rho e to the minus mu, 1 minus rho y. And that's for y greater than or equal to 0. Put a big check mark. We've seen that before. Okay. That little baby example shows you what the algorithm is. I'll tell you again. You take a star of minus s times b star of s minus 1. You know what that is. So you got the expression for that. You want to write that as a ratio of c plus over c minus. How do you do it? You look at the poles and zeros of a star of minus b star of s minus 1. Plot them. Everything in the left half plane goes with c plus. That's all you care about. And now you got the answer up here that basically c plus of phi plus of s. Once you got c plus, you got phi plus, and you're done. And the k you find, again, related to c plus. It's really very simple, except to find the roots. And I promise you over and over again, that's the only hard part. So I took you deep into it with a lot of terms you probably didn't understand, but just to prove that this is the algorithm you want. Now, I'm not going to take you through it today, but in the book, I do, I do GM1 as an example. And when I'm done, for W of y, I should get the known answer that we had, I remind you in the early part. Let's see, where is it? It'll be this equation right here, where sigma is found from here when m equals 1. Well, when you go through that example, you'll find that there is an unknown root. And it comes up in a slightly different form than appears here, but it's equivalent to sigma. So, and by the way, going through that example is a bit of a mess, because you have to use basically Richer's theorem. you got to pick an f of s and a g of s and show that f is greater than g all over. And it's a mess because things happen around the origin that you don't like. So it's all kinds of complexity. It's in the book. It's a detail. You got to draw a circle around the origin. You got to recognize that a vector there has a cosine and a sine depending upon the angle of the vector, blah, blah, blah. It's a mess. But it's all GM1. It's all of GM1. And you come out to the same answer you had here. So that's basically what I wanted to take you through. The important thing is to remember this algorithm. Again, in the algorithm I wrote up here. Where did I write it? And it's written very clearly in the book. This one right here. This is the algorithm. And the hard part is basically to find the poles and zeros of this and pull out the right ones for C+. And then you're done. Okay. So we have a few minutes left, because I skipped a bunch. I skipped GM1, but you didn't want to go through that anyway, did you? Or do you? Said no. Who's the fast no? That was you. Okay. But it's in the book. Okay. Now, a couple of administrative things. First of all, the final is on Monday. It's going to cover everything. It'll emphasize more chapters 5, 6, and 8. I skipped chapter 7. I'll talk to you about it in a minute. You can buy anything you want. There may be some things that you have to think as well as just regurgitate. You know, you may have to use your intuition here and there, and your knowledge of life, but we'll do that. What I want to do now is two things. One, I was told to remind you of this thing, that you get to evaluate me, okay? You have until 8 a.m. Saturday to log into MyUCLA and to complete the form. Do it. Do it. Be as mean as you want. Be honest, though, okay? Second thing, I want to tell you what we didn't do so far. What I did is I skipped, in chapter 5, I skipped any notion of the busy period. It's some beautiful work, but it's a bit detailed. It's all in the book. You might want to play with it because there's some wonderful ideas there on the physics of the problem and then some very good analytic work. One of the key ideas there is, if you look at a busy period, how long is it? That's the question. What's the distribution of the length of a busy period? By the way, what's the distribution of the length of an idle period in MG1? How long is an idle period in MG1? Come on. What is it? Exponentially distributed at rate lambda. Right. So that you know. Busy period, how long is it? But the observation is the duration of the busy period doesn't depend upon the order in which you served customers. Work keeps coming in, they keep getting spent at a second per second. So it's going to have a duration independent of what order. First come, first serve, last come, first serve, ugliest first, whatever. As long as you have what's called a conservative service algorithm. Namely, you can't throw work away before it's done. You can't create work. And you can't stop working while there's work to be done. In other words, you do work and it's done. You can't get rid of it. You got to do it. The notion of a conservative work. And that busy period is independent of the order of service. So our good friend Takács, the mad Hungarian, he said a very easy way to do that is to take last come, first serve. And it's a very beautiful argument for figuring out what happens. And I'll leave that enjoyment to you. Okay. But then, using busy period arguments, you can come up with the Pollaczek-Kinchin formula for the waiting time by looking at the busy period of first come, first serve. It's very nice. But anyway, So much so for making you want to look at the busy period. Okay? That will not be on the exam. There may be some simple ideas there, like I could ask what I asked you, what's the duration of the idle period? That you should pull out like that. I won't ask you that, but maybe something related. I also skipped combinatorial methods, another way to deal with MG1. And I skipped another approach to MG1 based on, again, Tarkach, something called the integral differential equation. In Chapter 7, I skipped something called the method of collective marks. That's lovely stuff. And I sort of referred to it earlier one time. I pointed out that it's possible to interpret transforms as probabilities. And I'll give you a little taste of it. Suppose customers come into a queuing system, and when they come in, some little gremlin there neither puts a red mark on them or not, independent of anything else in the system. He tosses a coin with probability P, you get marked red. 1 minus P, you don't get marked red. And you can ask questions like, what's the probability that there are no marked customers in the system at time t? Well, to do that, you have to ask, well, who came in, who got marked, who left, whatever. It's all thinking about the physics of the problem. You're not yet with equations. You know, the probability of 10 people being marked is P to the 10th. And if there was something not marked, 1 minus P to the rest of them. So you can use these probabilistic arguments. And by arguing that way, you can come up with some terrifically, happily complicated equations that you would just die to get if you were to write the transforms. Ends up to be a transform equation, because guess what? The probability of marking will be the probability 1 minus z, our good friend z from the z transform. And probably not being marked as z. And so when you get something with z to a power, that sounds like a transform, doesn't it? So by making these probabilistic arguments, you begin to get transform equations for free. Yes, right. Sure.
I guess it's agnostic to whatever the Q is, right? It can be for NM1 or GG.
Yes.
So,
By the way, has this failed? Still working?
it's still,
It's red. Okay. Okay, go ahead. Another example of where marking customers helps is the following. It leads you in probability theory, when you have two independent events, you want the probability of joint event, you multiply the probabilities if they're independent, right? In our transform domain, when you add together independent random variables, you can involve them, and when you transform that, you multiply their transforms. Multiplication of transforms, multiplication of probabilities. Yes, that correlation comes out beautifully when you think about marking customers. It's a wonderful recognition, adding together independent events. Okay, so you might want to read that. It's produced some very complicated results easily. Okay, then in chapter 8, I skipped Kingman's algebra for Qs. That's another approach instead of the spectrum factorization method. There are many ways you can do it. There's the Polycheck method. You know, GG1 is a complicated system, chapter 8. And we took one approach, but an approach I particularly like because it's really simple when you're done. We didn't touch volume 2. Now, volume 2 has the following chapters. In chapter 2, it's got a whole section on bounds, inequalities, and approximations. We've been getting exact results all the way. Well, you can't always get an exact result, so what do? You look for ways to get approximations, upper, lower bounds, inequalities. And there's a kind of message here that I want to give to you. And it's the following. Suppose I have the real world here, the real physical world. And there are some experiments I run, perhaps. So let's draw that real world over here. Now, as performance evaluators, as queuing theorists, what we typically do is we make a model of the real world. Model of the real world. MM1, that's a model. It's not necessarily exact, but it's a model of what's happening. GG1, a mechanical system with moving parts, kinetic energy, and all the rest. We make a model. And what do we do as evaluators? We try to solve that model, right? And suppose this is the solution to that model. You found the waiting time distribution or something, okay? But it applies to any analytic method. And when you've done that solution, how happy are you? You get an A in the course, but if you're out there working for AWS, you got this model, your boss is going to say, well, how do I know it corresponds to the real world? So you got to close the loop. You've got to come back here and ask, does that model predict behavior in the real world? We're going to measure things there. We're going to see what goes on. Okay, now, where do you often spend your time? You make a model, and you may have a really hard time getting an exact result. Some complicated, you can't factor the polynomial or something. So what can you do? As I said a moment ago, you can make an approximate solution. Bound it, approximate it, and then compare that to the real world. But there's something else you can do. And what is that something else? You can make an approximation right here don't make a perfect model of the real world, or as perfect as you can make it. Suppose you notice that the input is not Poisson. Assume it is. That's an approximation. So, and point is, if you approximate here, you may be able to get an exact solution to the approximate model, and that might be a better fit to reality than getting the perfect model and an approximate solution to that. So be aware all these places are available to you. We spent all our time going from an exact model to an exact solution. But as says here, in chapter 2, these are approximations, bounds, etc. And by the way, as a result of chapter 2, it turns out you're able to show that the long waiting times in GG1, the tail, is exponentially distributed. For long tails, which means long waiting times, turns out to be exponentially distributed, which is a nice result that comes out of the theory. Chapter 3 in that book is now about priority queuing. In what order should we serve people? First come, first serve, last come, first serve, priority ordering, tallest first, richest first. Maybe somebody pays for the order of service. How does the system perform in a case like that? And it turns out there's a very nice set of results that I was able to get. Conservation laws. I mean, look, suppose we have a priority queuing system, and you're the low priority guys, and you're the high priority guys. And I do better for them, so their waiting time goes down. Guess what happens to your waiting time? It goes up. If they go down by 10 minutes, how much does yours go up? Not necessarily. What is conserved when we play that game? And the conservation laws tell you exactly what's conserved. And I'll tell you what the answer is. It's the row, lambda over mu. It's the row weighted waiting times. Your utilization times your waiting time plus their utilization times their waiting times, the sum of those two is constant. It's a very nice result. That's what comes in chapter 2. Then in chapter 4, we go to computer time sharing, what happens when you not necessarily change things based on priority group, but on how long your job is. For example, shortest job first is the best algorithm for minimizing the average weight of a population. Because you want you don't want to make a little job wait for a long job. That's really bad for the little guy. But if you make the long guy wait for the little guy, it doesn't hurt the long guy very much. But you've really helped the little guy. So how does all that work? And what are the algorithms? A whole bunch there. Then finally, the last two chapters actually, all about computer networks and the internet and the ARPANET and modeling, etc. So that's what the class that I'm not going to teach is all about. Okay, so we have 2 minutes. Any questions? Yes.
Just, I guess, to go into a little bit about priority queuing and conservation laws.
One and a half left.
Okay, 1.5. Do you have any strong opinions one way or the other? Because it kind of touches on net neutrality. So do you want to be recorded saying anything political about that?
I've said it before, I don't think there should be discrimination on an arbitrary basis by the suppliers, but if you're willing to pay for more, is always the case, you can get better service. So if you want to buy a bigger bandwidth, okay, but don't do because, my name is such and such, is your name is such and such, or I'm coming from a particular location. It should be based on the economics and not on an arbitrary metric of discrimination regarding net neutrality. Make it ring. Okay, anything else? Good luck on the exam. Oh, by the way, some of you didn't like that I attached blank papers to the exam. Would you rather have loose papers so you can show the problem as you're solving it? A separate packet or a bunch of loose papers, okay. Okay, well, good luck on the exam. Now do that last homework. See? Do that last homework assignment I gave you. I'm not sure we're going to grade it, but just do it and look over the homework assignments. Some of the homework assignments were tough, and I left out the really tough problems that I could have given you. You may want to do those after you get your grade, okay, to really learn this stuff. That's why you're here, to learn, right? To get grades too, but that's why you're here, to learn. Okay. See you in the exam. Good. Thank you. Thank you.